In this video, we'll learn how to evaluate triple integrals in cylindrical coordinates. So let me just remind you or tell you that cylindrical coordinates, we obtain them by replacing our usual x and y Cartesian coordinates with the polar coordinates and keeping the z, the third Cartesian coordinate, as it is. So these cylindrical coordinates are just three numbers specifying each point in space, and the way their meaning is r and theta are your usual polar coordinates coordinating the xy plane, and z stays the same as it was. So a point in space has three cylindrical coordinates, r, theta, and z, and they are, well, r is its distance from the z-axis, or in other words, the projection of P to the xy plane has a distance from the origin, and that is r. Now, the line segment, the angle that this line segment from the origin to the projection makes with the positive x-axis, that's our angle theta, and z is just our usual Cartesian coordinate, the height of our point. Okay, so and just like we've seen with polar coordinates, there are some nice formulas connecting our usual Cartesian coordinates with the cylindrical coordinates. So x is r times the cosine of theta, y is r times the sine of theta, and z is, well, it's just z. So next, if we want to evaluate triple integrals, we have to remember their definition, and their definition as a limit of triple Riemann sums. And in those triple Riemann sums, the idea, the main point is that we subdivide the input space of x, y, and z into small subintervals. This way we form small rectangular boxes, and we take the volumes of those boxes, and for each box we take a sample point at which we evaluate the function, and then we just add these products up to get the triple Riemann sum. And once this the number of these sub-rectangular boxes goes to infinity, we get our triple integral. Now we do the same thing here with cylindrical coordinates. So imagine having some small changes in r, theta, and z, and what that entails, what kind of shape we will get. So let's say we take r, so and at some angle theta, and we add delta r to it. So that's at the distance r, and we add a small distance delta r. Same, we do the same with theta. We had theta, we add a small angle, well, I will exaggerate here, a small angle delta theta to that to obtain these points and this ray. So here we have a nice polar rectangle sitting in the xy plane. Okay, and then imagine that we are at some height z. Okay, sitting at some height z, and then so that's z, and then we add a small increment in the z value. So this way, what we'll obtain is a cylindrical cylindrical box there. So that small increment the small height was delta z. So if we now want to compute the volume of this box, of this cylindrical box, well, we need to find the length of its three edges. Well, this edge is delta z, so that's nice. But this edge right here is just the change in r, that's delta r. What about this edge, and the third edge? Well, it's the circular arc that we had there, with a circle of radius r and this angle being delta theta. So that circular arc will have a length of r times delta theta. Okay, so now if we take these three lengths and multiply them, we get roughly the volume of that cylindrical box. So let me write them as r times delta z times delta r times delta theta. So this is very important because this is the small change in the volume, I should say, is what enters the triple Riemann sum, and what, as we take the limit to obtain the triple integral, will turn into the volume element dv, but the most important bit is this factor of r, which is the same factor of r that we had in the polar coordinates. So that factor of r will enter our triple integral formula when we use cylindrical coordinates. So let me now give you this triple integral formula. So what happens when we try to when we evaluate the triple integral of a function of three variables over some region in 3D space? Well, let's say that that region can be specified by theta changing between alpha and beta, r changing between h1 theta and h2 theta, and z or z changing between two functions of x and y, so two surfaces. But let me write x and y in terms of r and theta. So it's r times the cosine of theta and r times the sine of theta, which are the arguments of our function u1, and similarly the top boundary, the upper boundary, is u2 of r times the cosine of theta, so x, and r times the sine of theta, so y. And then we have the function f with, now instead of x and y, I'm using the cylindrical coordinates, so it's r times the cosine of theta for x, r times the sine of theta for y, and z, of course, is kept the same. So all we have to do now is take care of this volume element, which comes from this argument out as r times d z d r d theta. Okay, so the innermost integral is is done with respect to z, then we integrate with respect to r, and then we integrate with respect to theta. But the very important thing to remember here is not to forget this factor of r in the formula. So this is our triple integral formula in cylindrical coordinates. Okay, so let me now give you an example. Let's take the function f of x, y, z equals x squared plus y squared, and let's evaluate this function over the region that is a cone whose apex is at the origin, and it lies above the circle of radius 2. Okay, just like that, with this angle being 90 degrees, so the slope of this face, this line, is 45 degrees. Okay, so let be this region, this solid cone, and it goes up to a height of 2. Let's compute the integral, the triple integral of this function over that region. Okay, pause the video and input your answer below. Okay, I hope you paused it and realized that b can be specified as follows. So theta can of course change between 0 and 2 pi. There is no restriction on theta. It always can go around in a circle. R can change from changes from 0 to 2. The distance from the z-axis as we climb the z-axis actually goes from 0 at the apex to 2 when we go all the way to this upper edge of the cone. And finally z, so when theta and r are fixed, what happens with the height function? Well, it can go from r, so this height is r, then this radius is r, from r to up to the height of the cone, which is 2. So it changes from r to 2. With this we can write down the triple integral using the formula that we have here. So theta changing from 0 to 2 pi, r changing from 0 to 2, and z changing from r to 2. And the function that we are integrating is x squared plus y squared. Now, if we use these formulas for the cylindrical coordinates, we'll see that x squared plus y squared is simply just r squared. Okay, so r squared is what we have for the function, but then we have an extra factor of r coming from the volume element. So that's multiplied by r, and then we integrate with respect to z, then with respect to r, then finally with respect to theta. So that's just r cubed, what we have there, r cubed. So let's integrate with respect to z first. So what we get is r cubed times z, with z changing from r to 2. Then we integrate with respect to r and then with respect to theta. So what's that is 2 minus r. So if we have r cubed multiplied by 2 minus r, okay, then we integrate with respect to r and then with respect to theta. Okay, so what we have here is 2r cubed minus r to the 4. So 2r cubed minus r to the 4. So when we integrate that with respect to r, we get 2r to the 4 over 4 minus r to the 5 over 5, as r changes from 0 to 2. Then we still need to integrate with respect to theta. So what we get here is twice 16 over 4, so that's 8 minus 35 over 32 over 5. So let me just jump right to the end. So that's giving us a value of 8 minus 35 over 32 over 5. So that's 8 over 5 times the integral. When we integrate with respect to theta, that's giving us an extra factor of 2 pi. So what we get here is 16 over 5 times pi. Okay, I hope you enjoyed this video, and I'll see you in the next one.